Section 3.3 is on page 120, talks about complex roots of the characteristic equation. Recall how we get the characteristic equation. In this case, if it is a second order differential equation, then that would mean that the characteristic equation is a quadratic. And quadratic could have one of three solutions. It could have two distinct solutions. That's what we did in section 3.1. It could have two complex solutions. That's 3.3. Or it could have repeated solutions. That's 3.4. Euler's formula. If I take E, remember what E is, 2.71 raised to the I theta. That's the cosine of theta plus I sine of theta. If you don't recall that as being complex numbers, that's okay. You probably remember this or this from your trig class, right? That would be section 4.3 if I'm not mistaken. 4.3 or 4.4, going from rectangular form to complex form, right? And this is the equivalent of AI plus BJ using vector notations. Those behave exactly the same, except in vectors you have direction. Here we're really not worrying much about that. And do remember, a to the x times a to the y equal a to the x plus y. If I can go in this direction, I could go backwards. So, number 1 through 4, use Euler's formula to write the given expression in forms of the complex number a plus bi. Well, this is the cosine of pi plus I the sine of pi. Cosine of pi is -1. Sine of pi is 0. So this is nothing more than -1. And if you recall from back in the days, you were to rotate to pi radians, and you would move 1 unit in that direction. If the base is not an E, well, we have a nice trick because we took 5B and 5C and college algebra. We know how to make that an exponential with a base of E. That's very easy to do. Properties of logs. That is e to the natural log of 2 times, minus, my mistake. I want to do this in 2 steps. Natural log of 2i. And by this property I just mentioned, this is e to the natural log of 2 times e to the negative natural log of 2i. This is simply a 2. And this is the cosine of negative natural log of 2 plus I times the sine of negative natural log of 2. That is 2 times cosine of natural log of 2 minus I the sine of natural log of 2. Reason for that, cosine is an even function, absorbs the negative, sine is odd, so the final answer is twice the cosine of natural log of 2 minus I times twice the sine of natural log of 2. Or you could put the I at the end. I really don't mind. They like to put the I up front. It makes no difference. It's the same thing. Now, we're going back to what we talked about. If I look at a differential equations, this is a linear differential equation. Did I give you a page number? Yeah, page 125. This is linear second order differential equation with constant coefficients. Well, what does that mean? That means I could let y equal e to the rt. I need y prime. We did that on every problem in the previous section. I am aware of that. And if you're sick of me writing this, well, guess what? I'm going to keep on writing it. Now, if I fill in the blanks, I'm looking at r squared e to the rt minus 2e to the rt times r plus 6 e to the rt equals 0. I'll factor e to the rt out. I'll have r squared minus 2r plus 6. E to the rt cannot equal 0. We know that already. So it must be that r squared minus 2r plus, I complete the square, students like quadratic, whatever works, take half of the middle number and square it. So however you were taught how to do this. If I square root both sides, I'll get plus or minus the square root of -5, which is 5i, and r will equal 1 plus or minus radical 5i. And this is probably a good time to introduce this theorem. So, given two complex solutions of the characteristic equation, if you've forgotten, this is the characteristic equation. Given two complex solutions, I just got two complex solutions right there. A plus bi, plus or minus the fundamental set. So when I want to write the fundamental set for this, that would be e to the at, e to the 1t, the cosine of radical 5t, and e to the 1t sine of radical 5t. And let me show you where that comes from. If I say now, based on my solution, so this is extra. If I say y equal e, and r is 1 plus or minus radical 5i t, y would equal e to the t, right, plus or minus radical 5ti. Y would equal e to the t times e to the plus or minus radical 5ti. This would be e to the t, and this will be the cosine of plus or minus radical 5t plus I times the sine of plus or minus radical 5t. And they prove in the book that whether you take the plus or the minus, you end up with the repeated roots. So what they do here, they say, well, you could just use this theorem. E raised to that power, you could write it like this every time until you get the hang of this. So if this is the fundamental set, that means this is a solution to that equation, and this is a solution to that equation, and those two are linearly independent. And the general solution will be what? Y would equal c1 e to the t cosine of radical 5t plus c2 e to the t sine of radical 5t. Sometimes you see the answers written this way, and the reason for that, if they want to find the limit as t approaches infinity, they could tell that this is an exponential and it's going to go to infinity. But either way will do. And that's what this section is all about. So if I look at number 8, the same deal. This is a linear equation with constant coefficients, right? I would say let y equal e to the rt, y prime is r e to the rt, y double prime is r squared e to the rt. So r squared e to the rt plus 6r e to the rt plus 13 e to the rt equals 0. Factor e to the rt out, you'll have r squared plus 6r plus 13 equals 0. Again, characteristic equation. E to the rt can never equal 0. It must be that r squared plus 6r plus, again, that doesn't factor. I'm going to move the 13 to the other side. I'm going to take half of the middle number, which is 3, and square it. R plus 3 squared will equal a -4. So r minus 3 equal plus or minus square root of 4 is 2i. And r will equal 3 plus or minus 2i. The fundamental set is actually e to the 3t cosine of 2t and e to the 3t sine of 2t. And the general solution would be y equals c1 e to the 3t cosine of 2t plus c2 e to the 3t sine of 2t. You could factor e to the 3t out if you wish, but that's sufficient. And what's left? What if they gave us initial conditions? Same deal. I see a linear differential equation, second order. I let y equal e to the rt, y prime is r e to the rt, y double prime is r squared e to the rt. This would be r squared e to the rt plus 4 e to the rt equals 0. E to the r, again, characteristic equation right there. E to the rt times r squared plus 4 equals 0. Actually, they talk about this being the characteristic equation, but it makes no difference. Since that could never equal 0, r squared equals 4, so r equal plus or minus 2i. So here, the fundamental set is actually cosine of 2t and sine of 2t. And the general solution would be y equals c1 the cosine of 2t plus c2 the sine of 2t. That does it. Except they gave us, in this case, initial conditions. So if I take y equaling c1 the cosine of 2t plus c2 the sine of 2t, y of 0, that is c1 times 1 plus c2 times 0, and that is 0. That indicates that c1 equals 0. So that's gone. And if I take y prime, the derivative is actually 2c2 the cosine of 2t, and y prime of 0 would be 2c2 times 1, and that equal a 1, c2 equal 1 half. So the solution to this would be y equals 0 times cosine is gone. That will be 1 half the sine of 2t. And that oscillates from negative infinity to positive infinity. Alright, and if I move to the next problem, number 14, it's a bit lengthy, that's okay. So here, if I look at a second order linear differential equation with constant coefficients, I let y equal e to the rt. Y prime will be r e to the rt. Y double prime will be r squared e to the rt. R squared e to the rt, oops, getting carried away there, plus e to the rt equals 0. So e to the r, again, this is the characteristic equation. E to the rt times r squared plus 1 equal to 0. E to the rt cannot equal 0. So r squared plus 1 equals 0. That means r equal plus or minus I. Fundamental set would be cosine of t and sine of t, because e to the 0 is 1. And the general solution, that would be y equal c1 the cosine of t plus c2 the sine of t. And if I proceed and figure out what those are, well, let's see. Y of pi over 3, that's gonna be c1. Cosine of pi over 3 is 1 half. Sine is radical 3 over 2. And that's gonna equal a 2. Which means c1 plus radical 3c2 equal a 4. And if I take a derivative of this, y prime would be negative c1 the sine of t plus c2 the cosine of t. And if I take y prime of pi over 3, again right there, that would be c1 times radical 3 over 2, but that's negative, plus c2 times 1 half, and that equals a negative 4, which indicate negative radical 3c1 plus c2 equal negative 8. So I have a system of equations. If I multiply the top equation by radical 3, that would be radical 3c1 plus 3c2 equal 4 radical 3. Add those. That would be 4c2 equal 4 radical 3 minus 8. And if I divide by 4, I'll get radical 3 minus 2. I got c2. Now if I take the first equation and I say c1 plus radical 3 times radical 3 minus 2 equal 4. So basically, I substituted this value right there. C1, oops, let me stick with the coloring, that helps a lot. C1 plus 3 minus 2 radical 3 equal 4. So C1 is 1 plus 2 radical 3. So my solution, my general solution right there becomes y equal, oops, right there. Y equals C1. C1 is 1 plus 2 radical 3 times the cosine of t plus C2, and C2 is radical 3 minus t times the sine of t. And there it is. And there's your homework. Section 3.3 on page 125. We're going to do number 1 through 15 odd.